So, hi and welcome to the Code Maven meetup group and to the Code Maven YouTube channel in case you're watching this in YouTube. My name is Gabor. I uh, provide training services in Python and Rust and help companies start using these languages. And I also think that it's important to share knowledge among people. So that's why I'm organizing these events, these meetings. And so I would like to welcome everyone who joined us at this meeting, and especially Miki for agreeing to give this presentation. And that's it. The floor is yours, Miki.
Okay, so
Go ahead.
hi everyone. I am going to share my screen. Then we will start. This one, share. Woo. Okay, so we are going to talk about what I call simulations for the mathematically challenged. And this is about the tool called simulation, how you can solve various problems
Sorry,
with
just
simulation.
just one thing. Can you move the button
Oh, the thing
again to this? Yeah, thanks.
moved. Okay, sorry. Okay, so my name is Miki. I've been a professional developer for 27 years now, give or take. Work mostly with Python and Go. I teach, I consult, I write books, I do videos, I enjoy myself in a very geeky way. And this is a tool that I used in a couple of occasions. I think it's very simple, but not a lot of people are aware of that. And it starts usually with a problem that you have, usually a data-related problem. You have a cache, you want to know what are the odds that there are given that amount of cache hits, what's the average latency, other questions that usually involved statistics or probability. And then you said, okay, we're all geeks, right? So we go and hit the books. And then you start seeing all these kinds of equations. And usually around that time, I say, you know what, maybe this problem is not that important, and I'll move to do something. And what I wanted to show you is basically that if you can write a for loop, you can do statistics. And that's it. You don't need more than that. You need the for loop and you need random. And these are the only two tools that you need in order to work. By the way, I'm going to show code, and if you have questions, feel free to ask. If you don't understand the code, if you want to learn about other things. So what are we going to do is we're going to talk about these 5 problems. So we're going to talk about the game of kata and what are the best tiles. We're going to calculate pi randomly, which sounds weird, but it's another interesting usage for simulations. We're going to solve the birthday problem, given 23 people, I think. What are the odds that 2 people in this group has the same birthday? We're going to see if person is sick, or what are the odds that this person is sick or not, given a test that says that he is sick. And we're going to talk about the Monty Hall problem, which is philosophically, it's a statistically interesting, but also a very philosophical question. Not a philosopher, so you can discuss it later and see what's going on. So let's start with Katan, right? So in Katan, we have these tiles, and every tile has a number on it. And then you throw a couple of dices. And if the number of the dices matches the number of your tile, then you can do things in the game. So at the beginning, you can pick out where you want to put your places, and it's up to you to decide which tile do you want, and you want to know, which tiles are going to get the most hits. What are the probability of doing that? So this is that. Yes, and I'm old. I'm using Vim. Sue me later, but I think the code is clear enough. So basically, what we're going to do is we're going to do a dice roll, which is basically just a random number between 1 and 6. This is coming from there. And then what we're going to do is we run a simulation. So what we're going to run a lot of dice roll. So I'm going to do 1,000,000 dice rolls. And every time I'm going to do 2 dice rolls, right? So I get a number, and I'm updating some kind of a counter, right? We have counter from collections. This is a special data structure that basically stores how much data we have per count. And then I'm going over all the numbers, right? The minimal number that you can get with rolling 2 dices is 2, with 2 ones. And the maximal one is 12, but the range is half open, so we're not going to get there. I'm going to show the fraction of how many this number of the total counts, and I'm going to print it out. And that's the code that I'm going to do. And then if you're going to do Python katan.py, you're going to see now we get probabilities, right? And you see that unsurprisingly 7 has the best percentage to get rolls of 2 dices. And you can do it what I call the hard way, which is just doing all the combinations of all the dice rolls and then calculate how many there are. But for me as a programmer, this is much easier. Right, I just write some code. This is like 20 lines of code, pretty simple. And now I have it. So this is the basic of simulation. We basically create scenarios using some kind of randomness in scenario. And then we are going to calculate some statistics about what happened on every scenario and finally display the result. And this is known as a simulation or a Monte Carlo simulation for what we have. Questions about this one? No questions. Right, by the way, if you ask a question, just open the mic and ask the questions, because it's hard for me to focus both on the code and on the Zoom screen. Okay, the next thing we're going to do, it's pretty interesting. We're going to calculate pi, again, randomly. So the way we're going to do it is we're going to say, let's take a circle which has a radius of 1. And now we're going to concentrate only on top right square, which is the bounding square for this circle. And we're going to start getting random dots. If the dot falls in the circle, I'm going to paint them as green. And if it falls outside of the circle, I'm going to paint them as red. Okay, so once I'm done it enough times, I can calculate what is the ratio between the green dots and the red dots. And this ratio is quarter of a pi. Right, because the area of the circle is pi r squared, but r is 1, so it's just pi. So basically, the amount of dots that falls inside the circle should be pi. But we doing it only on a quarter of a circle. This is a quarter of a pi, and we are going to get the number pi. So this is pi.py. So again, we're going to import this time uniform from random and then SQRT. And this is going to run for a bit, so I'm going to display a progress bar with something called TQDM. And then the radius is 1. And we have n, which is the number of iterations, which is 100 million. And inner is the number of points that are inside the circle, which I'm going to do with to start with 0. Right, so I'm getting x and y, which is uniform between 0 and 1. And then if the point falls inside the circle, I'm just going to increment inner. So this is how many points fell inside the circle. Now, the ratio is inner divided by n. And as we said, this is quarter of a pi. So we need to print out 4 times this ratio to get to the number of pi. Um, and you know what? I'm going to also run the time command to show you how much time it took. So this is 100 million runs. So it's going to take a little bit of time. And it's a good thing in the winter because it also warms up your CPU. So you can warm yourself without using the AC. All right, so TQDM, which shows the progress bar, is really nice, especially if you have long-running processes. You know if your process is actually running or it's not stuck somewhere. It's been done. And we see that we got 3.14, which is close enough to pi. And it took us about 41 seconds to run that. Now, one thing that can help you with simulations is PyPy. So if you're not familiar, the Python we are using is called CPython. It's Python written in C. There are other Pythons, such as Jython, which is Python written in Java, and several others, and MicroPython for micro devices. And there is PyPy, which is Python written in Python. And it has several optimizations that are not in CPython, especially a JIT compiler, though from 3.13 and up, we have an experimental JIT compiler in CPython, which should bring it up. And if I'm going to run a PyPI on that thing, you're going to see the difference, right? Oh, forgot the time command. You see this is 3.5 seconds, so more than 10 times faster on these calculations. So I'm not saying use PyPy for everything. There are some compatibility issues with especially external libraries and maybe other things, and it's not on par with Python. Currently, I think they're on 310, equivalent for 310, and right now in Python we are on 313. So they take some time. They're building up, and then they close it. But it's a nice tool to know and work with. Questions about this one?
It's not about this one, and probably it's not relevant to this presentation, but maybe it's for another time. Is how come actually that PyPI can be so much faster? I would really like to understand this.
The current CPython itself does not do any optimization to code. So if you look at the C compiler, it has tons of optimization, loop unrolling, constant folding, a lot of many things that the Python interpreter is not doing at all. And the other thing is that there is a technology called JIT, which is just-in-time compilation, which means that you run the code once in Python, you see what happens there, and then you generate specific machine code. And next time you call the function, it is actually not the Python function it's called, but the optimized generated machine code for that. And this is something that Node.js and other dynamic languages are using, including Java, to make things faster. And PyPy has a very good JIT compiler that has been developed for a lot of years, and that's why it's faster. Basically, PyPy is written in Python, but eventually it generates an executable in machine code, so it is pretty fast in this case. Okay, so someone joked that this is every time they go on a Zoom meeting, that's what comes to their mind, right? This is very similar to Zoom, and the idea is, and this is known as the birthday problem. Given a group of people, what are the odds that two people have the same birthday? And If what I pick up as a group size is 23 people. So I would like you to just take a guess. Like we have a group of 23 people. What are the odds that two people have the same birthday? So a random birthday. So I'm going to basically say that I'm not looking at dates. I'm looking at day of year. So we have 365 days per year. So a random date is basically a number between 1 and 365. That's how many days we have in here. And now what I'm saying is, given a group of a given size, are there any duplicates in the group? Right, so basically I'm creating a set and then going over the numbers, generating a random birthday. And then if you already seen this birthday, we say there is a duplication, so at least two people have the same birthday in that group. Otherwise, we add it to the group and return. And finally, if you're out of the for loop, we say no, there are no duplicates in this group. So basically, we draw a group of random numbers between 1 and 365 and say, is there an overlap here somewhere? Right, and now we start again the simulation. So simulation now is going to run over a million. We're going to do it 1,000,000 times. The group size is 23. And again, number of duplications is 0 to begin with. And then we run the simulation. And if there is a duplication, we say, okay, let's increment the duplication. Finally, we are printing what the fraction is from the total. Okay, so remember the number you guessed. Anyone guessed 50%? Right, seems pretty high, right? And this is something that happens with statistics and probabilities. A lot of time, this is not intuitive. A lot of times we think that we know the answer, and we say, there are a lot of days, only 23 people, how comes? But if you do it and you do the statistical computation, you'll get exactly the same thing. That's the idea. But again, this is a more complicated computation. And for me as a developer, this is pretty easy. A for loop, a random, I'm done with it.
Yeah, it's nice. What would be interesting, I think, is to see if you take 2 people, 3 people, and so on, up to 365 people.
Yeah.
And for each number to see this, the probability, and then graph that.
I'm pretty sure there is. If you go on the web, this is a really known problem. People have done it already. You can probably see the graph for that. But this is not exactly true, right? This is a joke, right? And the chances of a piece of bread falling on butter side down is directly proportional to the cost of the carpet, right? It's not 50-50. This is correlations to Mr. Murphy. And the thing is that not everybody is born or does not an average distribution on the days that you are born, especially if you're born on March 29, right? This is reducing the odds that you're going to have someone with the same birthday. So we have a model, and there's a saying by George Box, which I really believe, that all models are wrong, but some are useful, right? So it needs to be interesting enough, or the answer should be interesting enough, but not to give you a useful answer, but you can have a model. So I actually took some data from about birthdays in general, right? So no, this is US birth, right? So there's a CSV file that gives you what is the birthday per file. Oh, this is a Windows new lines, yay. So we have a year, month, day of birth, day of the week, and how many births there were per every one of them. And then what I'm going to do is I'm going to do actually weighted probabilities, meaning it's not that every day has the same probability, but I'm going to use these frequencies to do that. And here I'm going to switch over to tools from the scientific Python side of things. And these tools are Pandas and NumPy. And I'm using Pandas. If you're not familiar with Pandas, and this may be a topic for a different talk, or probably you already done it, Gabor, then this is a really, really great library for working with data. I'm using it to load the CSVs. So basically, I'm loading the birthdays from this CSV file, and I'm converting things to datetime, and then I'm saying that the birthday is the day and the month, and then I'm doing what is known as a group by to get all of the people that were born on the same day in the month, divided by the total number of probabilities, and then return the index and the values. So once I have that, I can do something else. I'm going to use now NumPy. NumPy has a random choice. Basically, choice says pick things from a group. And if you don't say anything, it's going to give an equal probability to everything. But you can provide it the size and the probabilities, and then it is going to do a weighted probability, meaning there's a bigger chance if more people are born on what is that, September 9, let's say, then there is a bigger chance it's going to pick September 9 versus February 29, let's say, or other day, April 26, for some reason. I don't know why. People don't like their birthday, or July 4th. I don't know why, but they have lessened. Okay, so I'm loading the birthdays from the CSV file. I'm doing again 100,000 this time simulations. The group size is 23 and duplicate is 0. And again, I'm doing the same for loop, and again the same thing that I'm doing here. And if I'm running this one, we got the same number. Right, this is rounding up. Pretty sure if I'm going to show more digits after the decimal, it is going to show more. You're going to see the difference. But the idea is that we added more. We made our model more accurate, but even the inaccurate model was good enough, right? It was good enough, and that's what saying that all models are wrong, but some are useful. You don't have to have exact distribution or exact information about your data to gain some insights which are correct from the data. And a lot of time you can do approximations, and statistically it's still good enough for you to do. Questions? No question. Okay. So this is about a question that actually they gave to doctors. They said that there is a test for a disease that has 5% false positives, meaning that in 5% of the people, the test will tell you that you're sick even though you're not sick. This is what is known as a false positive. And it says that it knows that the disease strikes about 1 person in 1,000 in the population. Okay, they said, okay, now we're taking a random test. We take a random person from the street, we make the test, and the test says this person is sick. what is the actual probability that this patient is really sick? Okay, and think about that with COVID, for example, right? They swap you for COVID and it says you have COVID. Now you're home, you're not allowed to go out. Sometimes, for other diseases, it might say that the doctor says, okay, you're sick. Now you need a treatment, maybe a violent treatment, maybe something which costs a lot of money. So they ask these doctors to see if they're actually basing their decisions on something which makes sense or not, right? So talking about true positives, right? So if I predicted that the person is sick and they're actually sick, this is what known as a true positive. We talked about false positive, which is person is said to be sick, but they're actually healthy. And we also have false negative, saying this is a person who is sick and we said that they're healthy. And we have a true negative, which is a healthy person, and test says they're healthy, right? Remember, positive is sick, negative, healthy. That's it. This thing is known as a confusion matrix. And on the confusion matrix, you can do a lot of calculations when you measure your models, especially prediction models. You start with the confusion matrix and then say, what is the percentage of true positive? There's precision, recall, and several other things that come to mind. I call it, I think the name confusion matrix is also very good because I always get confused by that. I need to go back and think about what every term is saying, but we do that. So let's have a look at the sigma. Okay, so I have a function for one in. So I want to say that one in 1,000, right? They said 1 in 1,000 is sick. So basically what they're saying, I'm drawing a number between 1 and n. And if this number is 1, and I can pick any number between n. So 17, 3, any number will work. I just need that 1 in n will happen. And now I'm going to say like this. There is a person. And if the person is sick, we are going to say that the person is sick. This is not specified in the equation, but this is the assumption. The assumption that there are no false negatives, there are only false positive. So if you are doing that, and they say if the disease is rated, we say we have a 5% false positive. So in 1 in 20 cases, this test is also going to say true. So if the person is sick, the test is going to say for sure you're sick. If you're healthy, there's 1 in 5%, 1 in 20, sorry, chance that the test will still say that you're sick, even though you're healthy. So now number of sick people and number of people who are diagnosed as sick are both starting at 0. And now we are running a million simulations. For every one of them, we are picking a person at random. So the chances of the person being sick, like we said here, and the disease strikes one of every 1,000 people in the population, right? So there's a 1 in 1,000 chance that this person is sick. And if the person is sick, then we increment the number of sick, and then we do the diagnosis for the person. And if we diagnose the person is sick, we increment the number of diagnosed. Okay. So now we have the number of people who are actually sick and the number of people who were diagnosed as sick. And we are going to print out this frequency that says what are the percentage of people who are actually sick from the people who are diagnosed as sick. Anyone care to guess? 2%. Ooh, see, you are good. Okay, so a lot of people are saying, this is what? right? The test is only 5% false positive. How come? So 95% it's okay, but still only 2% of the people are sick. So and think about that. Yeah, 1% divide 5%. That's 2%. So if you come to think about that, has a lot of implication. This is again this intuition that we have that is usually wrong when it comes to these things. And the sad thing is that they gave this test to a lot of doctors, most of them get it wrong. And then it means that they're actually basing treatments and other things on something which is not correct. So maybe they should run a simulation and get some understanding of what's going on. All right. Last one. The last one is known as the Monty Hall problem. And we are, okay, well, we have a lot of time. I'll start speaking, no. The Monty Hall problem says you're in a game show and you have 3 doors. And the host says, behind 2 doors, there are goats. And behind the 3rd door, there is a car that you can win. And it says, pick a door, 1, 2, or 3. And you pick a door. Let's say I picked 1. And now the host says, okay, he goes on to another door. Let's say this time door number 2, opens the door and shows you a goat. And now he says, do you want to keep your original door or do you want to switch to the second one? Right? So you have a strategy now to say, now I picked door number 1, I'm going to stay with door number 1. Or after they show me the door with the goat, I want to change my answer and I actually want to pick door number 3. So what is the strategy? What is the good strategy to work in this case? Should I use it on 1 or 2? So again, we are going to simulate it, right? So a random door is a random integer. And here what we're doing is that we say, does staying with the door wins the game, right? So we pick one door, which the car is under the door, and then we pick another door, which is the door that the player picked. Now, if it is the same door, it means that the player who says I'm going to stay is going to win the game. Okay, so I'm just saying if the car door is equal to the player door, then meaning that the stay strategy wins. And now I'm going to do a million simulations. I'm going to say that these are the number of wins that the stay strategy had, and these are the number of wins that the switch strategy had. And I'm going to run the simulation. And then if stay wins the game, I'm incrementing the stays. Otherwise, I'm going to increment the wins. And then I divide them by n. So what is the fraction of they won? And I'm printing out what is the fraction of times we won with staying and what is the fraction of things that we did by switching. Any guesses? Which strategy is better? So if you switch door, you have twice as much chances of winning than staying. And this is really counterintuitive because why? Right? I picked a door at random. There could be a car under it. The fact that someone showed me another door that I didn't pick has a goat in it shouldn't change that. But it actually does. And there's a lot of debate. If you Google the multi-hole problem with statistics, there's a lot of debate about what does it mean and are these calculations okay or not? For me, yeah, I have a strategy now. So if I see a goat, I pick the other door, and that's it. Okay, so you can read more on Wikipedia on the Monty Hall problem, and it. So that's basically, these are the 4 cases, and I hope I convince you that when you have these questions, don't shy away because you don't know the math, because you don't know how to figure out statistics. And a lot of time it will also help you because a lot of time our intuition when it comes to statistics and probabilities is usually wrong. We as people have good intuition about small numbers. When it comes to large numbers, we are really very bad at that. There's one statistician, Nassim Taleb, who says that every time he works with statistics, he needs to turn off this part of the brain that says, I know what I'm doing, and just trust the numbers. Right, so if you want to learn more, there is a great talk by Jack van der Plas. Jack van der Plas is an astrophysicist who's heavily involved in the scientific Python community. And he has, that's where I started, and he shows some other simulations and how to do statistics. You can read more about the Monte Carlo simulation in Wikipedia. By the way, I think even in Google Sheets and Excel, you can run Monte Carlo simulations, which is pretty awesome. Or in Excel, in Excel now we have Python in Excel, right? So this is great. And there's a library called SymPy if you want to do what is known as a discrete simulation. And SymPy basically for every tick tell you process to do something, and then you can simulate cars going and people crossing the road and cell phone towers and a lot of other things. Z, I'm not sure what your name is, but he said the simulation will not help you if the problem is not well specified, and that is true, right? So you need a good definition of the problem before you start. If you have a vague definition of the problem, then you can think about it any way you want. I'm not sure why you're saying that the Monty Hall problem is not fully defined, but we can talk about it later. Because this is just about picking a strategy to win, and I think the switch one is a winning strategy. That's it. All of this code is in my GitHub talks repo, so you can look at the code there. All of the things that I have there. I wrote a book on Python with quizzes if you want to buy it. And if you have questions, that's a good time to ask them now. No question. Gabor?
Well, I don't have any question either now. I already asked the ones I had. I just want to thank you and thank everyone who joined us. If you are watching the video and you reach this point, then please remember to like the video and follow the channel. And under the video, you will find a link to where you will have the link to this GitHub page, to this GitHub repo, and you will be able to also find Miki. I guess you also
Yeah. Feel
share
free
your link.
if you have any questions, I will answer.
Okay. So thank you very much.
Thanks,
And
Gabor, for organizing this.
you're welcome, and I hope to see you in other presentations.
Awesome. Thank you.
Bye-bye.
Bye.